Hello everyone, welcome to this online course on material science. This is lecture 26 in module 1 on magnetism. In this lecture, my plan is to estimate what is known as the molecular field strength. And this term, molecular field, is relevant when you try to understand the spontaneous magnetization. And in the last lecture, if you recall, we have three different types of spontaneous magnetization. But in this discussion, I will particularly focus on this ferromagnetic ordering, which is a spontaneous magnetization, where the magnetic moments align themselves in the absence of any magnetic field, right? But then the question comes that if the moments are aligning, there must be a field, some sort of magnetic field. And we are assuming that in the absence of any magnetic field, what aligns these magnetic moments is an internal molecular field, right? And that's what we usually denoted by BMF. And this internal magnetic field, which is a molecular field, is given by, in our model, some lambda is some constant times the magnetization. This lambda is positive for ferromagnetic material and lambda is negative for anti-ferromagnetic material. But those details are not important for this lecture. The important thing is that this molecular field, we want to estimate that what's the value inside the solid this BMF has so that it can align the moments. But note, I am not commenting about the origin of this molecular field because that requires a separate discussion and depends on different quantum mechanical consideration. But here, the simple assumption is that the moments align due to this molecular field, although we don't know yet what's the origin of this molecular field. Now, to understand how to model this molecular field, we need some help from our paramagnetic discussion. If you recall, in one of the lectures before, I have discussed the paramagnetic model using fully quantum mechanical considerations, right? And if you recall that when we use this quantum mechanical paramagnetic discussion, we found that the magnetization of the paramagnetic material was some saturation magnetization denoted by ms times the Brillouin function, right? And we have plotted this function. It has an index labeled by the jth quantum number and the argument was y. And if you recall, the y was given by the lambda g factor times the Bohr magneton times the j quantum number times the magnetic field divided by kBt. That's our relation. Now, how do I incorporate this molecular field here in this quantum mechanical paramagnetic model? Is that we can replace this B by B plus this molecular field. So we are assuming that not only we have some external magnetic field, we also may have some molecular field which is internal of the sample. So in that consideration, you can see the Y now changed into G mu Bj B plus BMF, right? You will see why I am doing this replacement. Now, for a ferromagnetic discussion, the external magnetic field is 0. So once you put B is equal to B plus BMF, now for a ferromagnetic discussion, you can say we don't have this B, that's 0, right? So now your Y has this form, that G mu B J and BMF. What is BMF? It's lambda times the magnetization. So that's our expression for Y, right? And from this expression, you can just rearrange term to write the m on the left hand side, then you will have kb g mu b j lambda, then we will have t and y, right? There's a reason why I'm writing in this fashion. Then you can see that's just some number, so it's kind of m is equal to some numbers times y, which is straight line, right? Now let's compare these two equations, this one and this one. So here we have m is equal to some Brillouin function times the saturation magnetization. Here m is a straight line. So we can plot both of this function, right? And let's plot both of this function. Before that, you can see that the slope of this straight line, right, depends on temperature. So you can change the slope of the straight line by varying different temperature. Now let's plot this equation and this equation simultaneously to see where some magnetization can occur in the absence of any external magnetic field, right? So here are the plots for these two functions. So we have three straight lines for three different t, and three different t are T is greater than Tc. Tc is the Curie temperature, and then we will plot T is equal to Tc and one for T less than Tc. So as we are varying three different temperatures, we have three different straight lines, and you can see their slopes are different, right? Because the slope depends on temperature. So that's the m is equal to this constant times y curve. And on top of that, I want to plot this curve. So that's our Brillouin function, right? This nonlinear thing. Now the question to ask is that you can see when t is greater than Tc, right? Then this curve and the Brillouin function never intersect with each other, right? Because this one has a larger slope, so there is no chance this curve will ever intersect with this nonlinear one. But when you plot the curve, the straight line at t is equal to Tc, you can see they differ in the high value of y, but now when you are close to the origin, the straight line slope and the nonlinear Brillouin function has the same slope, right, in this region. You can see that very clearly. And that's around t is equal to Tc. Now when you go below t less than Tc, so you're operating below the Curie temperature, you can see the straight line cuts the nonlinear curve in two different points. What does that mean? It means that in this point, if somebody asks you what is the magnetization, that's the amount of magnetization, right? That's the ratio m by ms. Here, that's the amount of magnetization. So below Tc, we have a spontaneous magnetization. That's the meaning that in this equation B is equal to 0, but even then we have two stable points where we have non-zero magnetization, and these are our spontaneous magnetization, right? Now, our plan is to estimate the value of this BMF from this curve, right? And how do we do that? Let's try to understand. So to do that, first you see that at t is equal to Tc, the slope of these two lines, right, the nonlinear one and the straight line are the same. So that's why what you see is that when t is equal to Tc, what is the slope of the straight line? From this equation, you can see that when t is equal to Tc, the slope is nothing but you replace this t by Tc. So we want to understand what is the slope of this line. So that's nothing but kb Tc g mu b j by lambda, right? So that's the value of slope of this straight line. And also, if you recall that a nonlinear Brillouin function, right? In that lecture, in one of the lectures, I have shown you can be linearized because it looks like near the origin it coincides with the straight line. And it happens for the small values of y. And recall that in one of the lectures, I have shown you that when y is very small, the Brillouin function can be approximated by this expression, where we have sorry about that. So that's the expression for linearized Brillouin function. And then you can see that as m is equal to ms times this Brillouin function, we can approximate, so this is an approximation, this function as linear one, ms, and then we have j plus 1 by 3j times y, right? So I'm missing a y here, so y here. So that's, I have shown you in detail how to approximate this equation. So have a look if you are confused. Now we have the straight line from the Brillouin function. That's another straight line, but now you can see m is equal to some number times y, and that's our slope of the linearized Brillouin function, which is this bit, right? So from this you have the expression for the slope, and these two slope, the linearized Brillouin function and the t is equal to TC straight line, they have similar slope. So now you can equate these two slope with each other, right? And let's do that. So if you equate these two slopes, one from the straight line and one from the so I think I have made a mistake here. It should be, there shouldn't be any j here. So that's the expression. So we don't have any j here. Sorry for this mistake. Now, once you have this expression from here, you have lambda times ms here. So let's find out what is lambda times ms. That's nothing but 3, you can see 3 kbtc, j gets cancelled, so we have 3 kb tc and the g factor mu b times j. And if you recall that lambda times ms is the molecular field strength, right? The maximum molecular field strength in our problem. So for that we can estimate the value of this field. We know what is the value of this Boltzmann constant, and let's say in this problem Tc is 1000 Kelvin, because you know what is the lambda G factor. The J is half here, so L is 0 in this problem, S is half, so L plus S is J, that's half. And once you know J, L and S, you can estimate the value of lambda G factor from the equation that I have derived in one of the classes. And just let me write it here for completeness, that once you know these values J, L and S, then you can estimate the lambda G factor from this expression, SS plus 1 minus half L plus 1. So here is 0, this part get cancelled, you can put the value of S here, that's half 3 by 2. You know what is the value of J, find out the value of G. So everything is known here, Bohr magneton is standard, it's constant. If you put all the values, the surprising result is that the molecular field strength is of the order of 1500 Tesla. That's really surprising, because what this problem is telling you is that to align the moments inside the ferromagnetic material, the internal strength of the magnetic field is of the order of 1500 Tesla. That's like no experimental lab in this world can produce that high magnetic field. And just to give you some examples, the MRI use 1.5 Tesla, right? The standard medical instruments. So this is a ridiculously high magnetic field inside the solid, which are aligning the moments, and yet we don't know what's the origin of this magnetic field. So this is another kind of indication that you should understand, is that the reason why it's really difficult to put any classical picture to understand the ferromagnetic modeling is that this amount of high magnetic field inside the solid cannot be explained using any classical theory. Another point to understand is that usually this molecular field theory was proposed by Weiss. So this model is usually known as the Weiss model, where molecular field theory. But Weiss was really embarrassed, because when he proposed his model that this molecular field should align the magnetic moments inside the solid, he really did not know what was the real force behind this alignment. He assumed that there is a magnetic field and he named it molecular field. But what's the real origin? It turns out that after 30 years later, Heisenberg first introduced what really is causing this alignment, and this has to do with the exchange interaction between the electrons. So that's our next topic of discussion, that to understand the ordering of moments inside the solid, you have to understand what is known as the exchange interaction. And I think for this lecture, the central line is that the molecular field has a ridiculously high strength inside the material. It turns out, it seems from this problem, but we really don't understand how inside a solid this high magnetic field can ever be produced, right? So that's really a contradiction, and it was kind of, this puzzle was solved by, as I mentioned before, by Heisenberg. So I think for this lecture, and that's about it. And have a look at this problem, and then you have to go through some previous lectures to get acquainted with the many expressions that I have used in this lecture. So please go through the discussion of paramagnetic material in one of the previous lectures here. I think that's about it for this lecture, and thanks for listening.